Hello guys and welcome in this new tutorial. From this lecture until the end of this section, we are going to learn about the different equipments that are used in industrial design. This introductory section is going to be really important for you in order to understand how individual automation parts work, like motors, power supplies, fuses, circuit breakers, relays, contactors, and few more. So in this lecture, we are going to talk about motors, their type, and what are the important characteristics that we will need while we are designing an industrial system. So motors come in different sizes, and the size depends on how much torque you need in order to operate a certain machine. But from an electrical point of view, we look at the power consumption of each motor. They start from a few hundred watts to a few hundred kilowatts actually. And for each rating, we need to choose the correct equipment in order to protect that motor. There's thermal protection and magnetic protection, which we will talk about later. Now let's see the types of motors. Motors may operate on AC or on DC. But for heavy machinery control, usually AC motors are used. And like any AC system, there is two types, a single-phase motors and a three-phase motor. And the question is where to use each of these types. In any big factory, most of the time you're going to see three-phase motors. Three-phase motors operate really smoothly compared to single-phase motors. Also, they draw less current, which means they consume much less power than the single-phase motors. Now, there is a really important advantage for the three-phase motors, which is you can easily change the rotation direction. All we need to do is to change the phases order. Where in single-phase motor, we will have to get a special equipment and connect it to our motor in order to reverse the direction. But when it comes to manufacturing machines, we will see most of the time three-phase motor. So we might see it in washing machines, in dishwashers, or any home appliances. And we don't see single-phase motors a lot in factories or in heavy machinery. Now let's talk about the most important characteristics that we will see in AC motors. Maybe the most important one is the inrush current. So when you deliver power to your motor, there is an excessive amount of current that is going to be drawn. So typically this inrush motor is gonna last until your motor reaches its full speed. And we can approximate this inrush current to be in between 3 to 6 times the nominal current your motor is usually gonna draw. This current is gonna last for a few seconds or a few milliseconds. It depends on the type of the motor, and also it depends on how large your motor is. So if your motor usually draws 2 amps, you might see 12 or 10 amps in the first few seconds before it goes back to the 2 amps that is usually drawing. So we can use this information about the inrush current in choosing the thermal and the magnetic protection for the motor, which we will talk about later. It's also important in choosing the correct actuator for that motor. There is an important parameter that we need to calculate while we are trying to design a motor driving system, which is the current consumption. First, we need to know what is the power consumption of a three-phase motor. The relationship is given as we multiply the voltage by the current by cosine Q or theta times 1.73. While we are designing, usually the current is the unknown parameter that we need to calculate. And the voltage here, it could be 380 volts, it could be 220 volts. You need to check the power rating for three-phase of that motor. Now, power factor is going to determine how much of the energy you are giving to that motor is being used in reality. So your expectation is that it should use all the power you are giving it and there is no loss. But that's not the case. All the motors has some losses, and this loss is going to be represented in this cosine theta. the value of cosine theta is going to be in between 0 and 1. And here is something. If the motor is not loaded and it's not connected to any machinery parts, the power factor is going to be in between 0.2 and 0.4. And once we connect it to a real load, the power factor is going to be in between 0.7, 0.8, 0.9. It depends. The logic behind this, that if the motor is not loaded, it will not use all the power. It does not need all that power, so it will use only a fraction of it. That's why we'll have a really low power factor. But once the machine is loaded, the motor is loaded with the machine, well, the motor is going to consume much more power and the power factor is going to be improved. Usually in our calculations, we use a power factor of in between 0.6 to 0.7. Here we are going to go with 0.7. This 1.73 is because we have a three-phase motor, which is the square root of 3. If you want to look at the math behind this, I strongly advise you to check some articles about three-phase and the math behind it. Now let's have an example. We have a 1.5 kilowatts motor, and we need to calculate the current consumption of that motor. So we will rearrange the formula given above to calculate the current. We simply take the power and divide it by the voltage times 1.73 times the power factor, which is cosine theta. Our power is 1.5 kilowatts, which is 1,500 watts, over our voltage is 380 volts here, and we have the power factor of 0.7, and we multiply it by the 1.73 to get 3.25 amperes. And note that this is not the inrush current, this is the nominal current and the current that is the motor using during the normal operation. To know what is our inrush current, we can check the data sheet, or we can take the nominal current and multiply it by 6 times to get an approximated inrush current. Now, the final type that we will talk about is the servo motors. When we don't have a continuous rotation of a machinery and we need to accurately drive the machine to a certain point in space, we use servo motors. So it's usually used in motion control, where you can exactly know how many rotations did that motor rotated. Hence, you can tell the exact machine position.